products like this, it's easy to develop a concern for preserving the environment. But even in densely populated cities and everywhere in between, more and more people are becoming more and more active in efforts to preserve even basic things like clean air and water, a benign climate, and all the environmental benefits that we've taken for granted in the past. I'm not sure anybody can solve all the problems at once, but for our part at FIT, we've been pioneers in the use of biopolymers and fibers, starting with polylactic acid more than 20 years ago, and following up with PTT right after that. Then in 2008, when the price of oil collapsed, it seemed that interest in biopolymers declined a little bit, but more recently we've seen resurgence of that interest. We suspect many of our customers are seeing this interest as well. And so we've put together this summary of many different ways that we can work with you to develop profitable, environmentally advantaged fiber products to address your customers' concerns.
You're probably familiar with this sentiment. This is how many consumers express an interest in environmentally advantaged products. But green can mean a lot of different things. For instance, in many cases, a desire for a green product means a product with a reduced carbon footprint. In these cases, the principal concern is usually to mitigate the effects of climate change. But it's not the only thing the term green encompasses. There's also landfill proliferation, the direct cost of landfilling itself, concerns that the land could otherwise be put to more productive use, and the fact that to the extent that waste products contain toxic materials, those toxins are concentrated in one place, and a release from the landfill thus has a potentially higher impact. Microplastics are another environmental concern that falls under the umbrella, concern that's risen only recently but is gaining attention. Another relatively recent concern is marine plastics. We've all heard about the giant island of floating plastic trash in the Pacific Ocean that's the size of Texas. The term green can also mean a focus on reducing the hazard of malignant materials delivered in plastic products, whether these are directly toxic to humans or more peripherally malignant, such as genetically modified organisms, in particular with reference to bio-based polymers. Sustainability is another term that sometimes is used interchangeably with green, but used precisely, it refers to a concern with the depletion of limited resources. In most cases, this means oil, but can also refer to land or clean water or other resources. Related to sustainability is a concern for resource security. If the materials in a product affect a population's access to critical resources, this affects sustainability for that population, even if it doesn't affect the sustainability for others. This is especially critical if it affects the food chain for that population. And finally, there are potential concerns for whether the materials used in a product or its production process negatively affect a disadvantaged population. This is not necessarily directly related to environmental concerns per se, and it's still a peripheral concern, but it's probably wise to be prepared for this to become part of the discussion in the future. And when you look at the details in responding to any of these concerns, one thing that becomes apparent is that attempts to address any one of these may well have repercussions, sometimes negative repercussions, in one or more of the other areas. So it's important to determine up front exactly which problem or problems you want to address with the highest priority. Here's an example of what I mean by this. Let's say your primary interest is in reducing your product's carbon footprint. The problem with legacy oil-based polymers is that they take carbon that has been sequestered in fossil materials, principally oil, for millions of years, and at the end of the product's life, that carbon is added to our environment, increasing the amount of carbon dioxide and exacerbating the greenhouse effect. Eventually, over hundreds of years, these materials will finally degrade naturally, releasing carbon dioxide in the process. So, here's one way to reduce the contribution our products have toward increasing the greenhouse effect. If a polymer is not made from oil but is instead made from biological materials, the carbon is not fossil carbon, but new carbon that was already in the environment. If the polymer then is biodegradable, this carbon quickly returns to the environment without adding to greenhouse gases and is ultimately available to be reused in growing new plants as a source for new polymer. This is a fundamental concept sometimes referred to as sustainable or circular mass balance or a zero carbon footprint. Now, I should note that in the real world there are inefficiencies associated with this approach. Crops are grown with fertilizers and hormones and pesticides that can be hazardous. They're planted and harvested and transported with machinery that often runs on fossil fuels. So zero carbon footprint is never truly zero, but the carbon itself in the product itself may come close. And in many cases, the total cradle-to-grave or even cradle-to-cradle analysis reveals a carbon footprint that is at least less than that of products made with oil-based polymers. The circularity or sustainability of this approach is an attractive concept, and it's often seen as an ideal approach to the problem of accumulating greenhouse gases. But recently, there's been a lot of progress in durable biopolymers. These are polymers that are also made from biological materials, so the carbon comes out of the atmosphere rather than fossil deposits. But these polymers are not biodegradable, so they often end up in a landfill. And when they don't end up in a landfill, they're often dispersed as pollution. So they tend to exacerbate problems with landfill proliferation or microplastics or marine plastics. But if your primary concern is reducing the carbon footprint, notice that this approach takes carbon from the atmosphere and sequesters it in a way that it will not release the carbon back into the atmosphere for a very long time. So for the short and medium term at least, this approach actually has a negative carbon footprint, at least in the nominal case, ignoring all the imperfections that deviate from the ideal concept. And if the product can be recycled instead of landfilled or dispersed as pollution, the eventual decay and release of the carbon can be even further delayed, resulting in a potentially even more virtuous impact on greenhouse gas levels. So, if your primary goal is CO2 reduction, maybe you decide whether increased landfill use or increased plastic pollution is worth the benefit of reduced CO2 in the atmosphere. Or if you want to address carbon footprint but are also concerned about landfill use or marine plastic accumulation, maybe a more circular approach is preferred, even at the cost of less than maximum CO2 reduction. Another conclusion from this analysis is that in certain cases, landfilling may not be purely evil, but can provide some benefit to balance the costs. Even more intriguing is the idea that recycling, which is often seen as lower value, may actually have the potential to be a very valuable piece of this puzzle. So this suggests 4 categories we can consider for most polymer materials that can be used in fibers. The first is the legacy polymers, which are made from oil and are not biodegradable. Over the very long term, these are not good for reducing CO2 in the atmosphere, but it is at least possible to observe that these polymers sequester the fossil-based carbon for a very long time. The second category is oil-based polymers that are biodegradable. Some of you may not be aware that such a thing exists, but we'll discuss some examples, such as those listed here in a moment. From a carbon footprint perspective, these may be the worst choice of all, since they're made from fossil carbon and then release this carbon into the atmosphere much more rapidly than the legacy polymers. But if your primary objective is to address the presence of microplastics, marine plastics, or landfills, then these offer a benefit over the legacy polymers. A third category is biodegradable polymers that are made from biological sources rather than oil. These are the polymers that enable the sustainable model, or circular mass balance. And finally, there are bio-based polymers that are not biodegradable. This is the category that enables a nominal negative carbon footprint. The non-legacy categories here broadly form the group of materials known as biopolymers, and we'll soon take a look at some specific examples. One of the fundamental points here is that there are many different issues to address, but there are also many different solutions. And with proper knowledge of the available options, we can better design fibers and fabrics that can most effectively mitigate the problems of greatest concern. Among these solutions, let's take a look first at bio-based polymers, or polymers made from biologically generated raw materials. Among bio-based polymers, there are those that are bio-based and biodegradable, and those that are bio-based but durable or not biodegradable. We'll also take a look at some special cases and then briefly touch on natural fibers and cellulosic polymers. The best known bio-based and degradable polymer is PLA, polylactic acid. I mentioned in the beginning that FIT partnered with NatureWorks beginning more than 20 years ago to develop fiber process for PLA polymer. So by now, PLA is becoming a relatively mature product, at least in the biopolymer space, and in large part because of that maturity, it has a relatively low price. Large part of the cost reduction from economies of scale have already been achieved. Not all, probably, but more than is the case with most other biopolymers we'll discuss. PLA has become enough of a success story that current demand outstrips supply, so there are some supply constraints that may factor into near-term considerations, but this is not a situation that's expected to persist. With a melt temperature of 167 degrees C, PLA is generally useful in the same temperature range as polypropylene, but it is worth mentioning that PLA is also available with lower melt temperature. PLA fibers have high resilience and good strength, along with exceptional UV resistance and a level of inherent flame retardance. PLA is commonly known as a biodegradable polymer, but that degradation requires composting, and that generally means industrial composting, as home compostability is limited. PLA is also sensitive to hydrolysis, which renders it poorly suited to applications that require durability in hot and humid conditions. PHAs are a class of bio-based and degradable polymers that have been under development for some time and which may be beginning to show some signs of significant potential. Among a wide range of polymer chemistries in this class, the two that have shown potential for use in fibers are PHBV and PHBH. PHBV is marginally useful in some blends perhaps, but PHBH has some potential to be a big star. Most recently, Danimer has announced a line of branched PHAs that may be able to overcome some of the processing issues that have held PHAs back from fiber applications in the past. Melt temperatures for PHAs range from about 100 centigrade to about 180. The melt temperature for PHBH is 142 degrees, which is between the melt temperatures of polyethylene and polypropylene. Unlike PLA, composting is not required for these polymers. They are spontaneously biodegradable. This is not all positive, as it introduces some durability concerns depending on the application. But most intriguingly for PHBH in particular is that this means the polymer is marine degradable. So in the ocean or any other microbially active body of water, the polymer will relatively quickly degrade into CO2 in water. Also intriguing is the fact that PHAs are so chemically simple that they can be made from a huge range of biomaterials. This means that plant waste or weeds can be used rather than materials that otherwise could be used for food. There's even development work underway to produce PHAs directly from CO2 scrubbed from smokestacks. If those efforts are successful, I think the process will be one with an unprecedented level of sustainability. Here are a couple charts provided by Kaneka that illustrate the degradability of their PHBH. On the left is a chart showing the degradation over time under composting conditions. PHBH degrades more rapidly under composting than cellulose. And the chart on the right shows the degradation rate of PHBH in a marine environment. In water, PHBH degrades at the same rate as cellulose, but I suppose one of the important points Kaneko wants to make with this chart is to show that PLA does not degrade at all in water, at least at 35 degrees centigrade. Another commercially available class of bio-based and degradable polymers is made up of PBS and PBSA. Currently, only the succinic acid monomer used in these polymers is bio-based, so the resulting polymers are only 50 and 35% bio-based respectively. Their mechanical properties are comparable with polyethylene and polypropylene, but they have struggled to find applicability at 100% in fibers. Instead, their primary use seems to be in blends with PLA. Melt temperatures for these polymers are relatively low, which is part of the reason you tend not to see 100% PBS or PBSA fibers. Like PLA, these fibers are biodegradable but require compost conditions for degradation. Finally, among the bio-based and biodegradable polymers, polyglycolic acid has a relatively high melt temperature, which is combined with the unusual property of being water-soluble. PGA is 100% bio-based, but is only available for one source that I know of, and that supplier is currently restricting the availability of the polymer. So those are some bio-based polymers that are also biodegradable. Now let's look at some of the bio-based polymers that are durable or non-biodegradable. Probably the best known of these bio-based durable polymers is PTT, or polytrimethylene terephthalate. Only the propane-diol monomer is bio-based, so the resulting polymer is only 27.3% biosourced carbon content. So there is an asterisk involved when this polymer is classified as a biopolymer. But it offers properties closer to those of the legacy polymers than most other biopolymers. It has good resilience and is well suited for use in carpets. It also has a very slightly elastic behavior. PTT's chemistry and its properties fit in the space between PET and PBT, and it has a melt temperature of 228 degrees C. PET polyester is by far the highest volume fiber polymer on Earth, and it's actually possible to make PET from biomaterials. Despite PET's giant gorilla status in fibers, consumption volumes are probably even larger in drink bottles. So it's important to note that Coca-Cola began a project several years ago to eventually ship all of their drinks in what they call plant bottles, or bottles made with bio-based polyester. Early on, bio-based polyester was made using bio-based ethylene glycol reacted with petro-based terephthalic acid for only about 20% bio-based carbon content. More recently, a 100% bio-based polyester has been commercially produced. It's either difficult or impossible to find availability of this 100% bio-based polyester, possibly because it's all being consumed in bottles. It's also possible that bio-based polyester could be displaced in drink bottles by PEF, a new polymer we'll discuss next. Bio-based PET melts at 255 degrees centigrade, which is exactly the same as petro-based polyester. And that's an important point. Each of the bio-based versions of the durable legacy polymers can be expected to have properties essentially identical to the petro-based versions. With biodegradable polymers, it may be necessary to accept some reduction in properties compared to legacy polymers, and depending on the application. But with bio-based durable polymers, usually there's no reduction in properties. I mentioned PEF as a polymer that could displace polyester in drink bottles. If it does so, it could also be useful in a lot of fiber applications. PEF is 100% bio-based and not biodegradable. Its properties, the properties are comparable to slightly lower than those of polyester. But where it really shines is in its vapor barrier performance, which is significantly higher than that of polyester. In 25 years of developing new fibers, I have yet to find a fiber application that requires vapor barrier performance. But the reason this property is important to fibers is this. Coca-Cola is investing heavily in their plant bottle project. They are very serious about converting their immense consumption of polyester to a bio-based polymer. And if vapor barrier is not important in fibers, it's essentially the whole ballgame in drink bottles. So you can see that PEF has a lot of reason to hope for a successful transition from a developmental effort into a commercially successful product. That's what's important to fibers. A lot of interesting developments struggle to make that transition, but PEF looks like one that has a good bet to succeed. And once it's successful, it should be available for fiber applications and should bring a portfolio of properties comparable to those of the most widely applicable fiber polymer in the world. A couple of other factors in PEF's favor: it can be recycled in existing polyester recycle streams, which means that additional recycling infrastructure doesn't need to be created for a new polymer. And PEF can be produced in existing PET polymer plants, so new plants don't need to be built if an existing polyester producer wants to produce PEF by simply changing the raw materials they use. PEF's melt temperature is 230 degrees centigrade, a bit below that of polyester, but still high enough for most fiber applications. PEF is currently under development, and as early commercialization begins, the available volumes will probably be dedicated to bottle applications. But eventually, this could become a very promising biopolymer for fibers as well. After PTT, probably the best known durable biopolymer is biopolyethylene. 100% bio-based high-density polyethylene has been available for many years, and more recently, 100% bio-based versions of linear low-density and low-density polyethylene have become commercially available as well. Another recent commercial introduction is 100% bio-based polypropylene. Early volumes are somewhat limited, but they're growing. So I want to make sure our customers understand, for those of you buying polypropylene fibers or bicomponent fibers made of polypropylene and polyethylene, we could make a 100% bio-based version of those fibers for you today with essentially zero loss in properties. There are also some rather specialized nylon polymers that are 100% bio-based and commercially available. Among these, nylon 5,6 has a lower moisture regain than nylon 6 or nylon 6,6, and nylon 11 is pretty expensive, but if you want impressive copy for product labeling, consider this. Nylon 11 is probably the first green synthetic polymer. It's made from the castor bean, and the castor bean is grown in India in a region where almost nothing else will grow. So nylon 11 supports farming in an entire region that could be economically depressed without the castor bean, thereby adding a social equitability story to the carbon footprint reduction. The polymers I've already discussed are the primary bio-based polymers we might consider for a specific fiber application, but there are a few special cases that might be worth mentioning. First, as I've already discussed, bio-based polyester is technically feasible, but not currently available for fibers, as far as I can tell. But it's worth mentioning here because PET is such an important fiber polymer. Next, there are bio-based thermoplastic polyurethanes and bio-based PVC, both of which are commercially available but are rarely useful in fibers. However, if there is a fiber application that can make use of polymers like these, FIT is the right company to develop the fiber for that application. Bio-based nylon 6 and nylon 6,6 and also bio-based PBT are currently under development and will expand the range of properties offered by bio-based polymers in important ways once they're commercialized. Novamont is developing a broad and potentially interesting range of bio-based polyesters that are not necessarily directly analogous to existing petro-based polymers. They're looking for development partners, and this range of polymers seems to be worth watching. Finally, ultra-high molecular weight polyethylene fibers like Spectra and Dyneema are not made by melt spinning, so those are fibers that FIT can't help you with. But if you're using or considering petro-based versions of these fibers today, it may be worth knowing that bio-based versions of the fibers are commercially available. While I'm discussing fibers that FIT can't make, I should probably also mention that natural fibers are, of course, also bio-based fibers. We're all familiar with cotton, wool, silk, and flax, which is used to make linen fabrics, but there are a variety of less common natural fibers that are also used in certain applications, including those listed here. As I said, FIT can't supply these fibers, but there's growing interest and potential for thermoplastic composites that are made by blending natural fibers like these with synthetic thermoplastic fibers. and especially bicomponent fibers. You melt the thermoplastic fibers to become the matrix of the composite, and then the natural fiber becomes the reinforcement. If bio-based thermoplastic fibers are used, then the result is a bio-based composite. Additionally, there are natural bio-based materials that can be used as polymer additives in synthetic fibers, materials like calcium carbonate and nanocellulose, which can displace petro-based polymers in the fibers while at the same time enhancing their performance. Finally, in discussing bio-based polymers, I should probably also mention cellulosic synthetic fibers. The most common of these are viscose fibers. They're made from cellulose, and they are compostable. But because they are extruded in an organic solvent, these fibers are generally not considered environmentally advantaged fibers. Cellulose acetate fibers are found in most of the world's cigarette filters. They are also made from cellulose, although they degrade very slowly. The melt temperature for cellulose acetate is 225 degrees centigrade, which is high enough to be broadly useful, but melt spinning of these fibers is not yet a realistic possibility. And while a melt spinnable cellulose acetate is occasionally under development, I believe those efforts are currently on hold. We've looked at bio-based polymers, but that's only part of the biopolymer story. For the rest of the story, we'll look at some biodegradable polymers. There are 5 topics we'll discuss to describe the biodegradable polymers landscape. The first 2 concern the distinction between biodegradability and compostability. Biodegradable is a term that has 2 meanings. Technically, everything can eventually be decomposed by microbial processes, so in that sense, everything is biodegradable. But for our purposes and for the purposes of regulatory control and advertising claims, the time scale is important for distinguishing between things that are biodegradable and those that are not. In this sense, biodegradability generally requires complete or substantial decomposition into carbon dioxide and water under ambient conditions within a period of 90 days or less. One relevant test method is the OECD 301 test, which requires at least 60% conversion within a 10-day window and a total test time of 28 days. A compostable material is one that is biodegradable, but only under specific conditions of heat and humidity. The product must decompose into carbon dioxide and water in a specified time. The ASTM D6400 test is one that's widely used to certify a specific level of compostability. It's important to note that many consumers may be familiar with composting from their home composting efforts, but in a lot of cases, a material that's properly deemed compostable may only meet the test specifications if industrial processes are used. A third type of degradability is sometimes discussed alongside biodegradability. Oxidative degradation is accomplished without microbes and often breaks plastics into small particles which may not degrade further and thus remain potentially harmful, in particular as microplastics. And for this reason, many experts do not consider oxidegradation to be an environmentally friendly technology. Recently, a new technology has been introduced that seems to fit in between truly biodegradable materials and those that are typically considered not biodegradable. This technology involves the use of a polymer additive that enhances access to the polymer by microbes, thereby speeding up the otherwise very lengthy natural degradation process. Initial tests indicate that full degradation using this additive may take about 10 years, which is clearly much slower than accepted definitions of biodegradability, but it's still a significant improvement over a timeline of several centuries. This technology has the advantage that it seems to work with a wide variety of polymers, converting them from non-degradable polymers into those that, if not degradable, are at least much less non-degradable. And the polymers for which this option is effective are those that already provide reliable properties and which are available at low cost. So, while the environmental benefit may not be as great when compared with biodegradable or compostable materials, In some ways, this may be a more commercially viable step in the right direction. The end products of this degradation process are generally carbon dioxide and water. So this option is intriguing in a lot of ways, but I still have a question about whether this technology also generates microplastics along the way to a total conversion that may not be complete for several years. We've already discussed some biodegradable materials when we discussed bio-based materials. These materials listed here are those that are both bio-based and biodegradable. And these materials offer the most sustainability or the most circular carbon mass balance. Less well known is this class of materials, which are biodegradable despite being made from oil. PBAT is compostable. It's amorphous, which is often an undesirable trait in fibers, but can be advantageous in certain applications. Because it's amorphous, it doesn't have a well-defined melt point, but is effectively molten at temperatures near 120 degrees centigrade. Otherwise, its properties are similar to low-density polyethylene. Polycaprolactone has a very low melt temperature at 60 centigrade and is water-soluble. Polyvinyl alcohol is also water-soluble, with a much higher melt temperature at 200 degrees. Finally, the degradation-enhancing additive we just discussed doesn't typically achieve degradation rates that qualify for the term biodegradable, but it does dramatically improve the degradability of otherwise highly non-degradable polymers. So I've included these materials here with a question mark. Finally, of course, the cost of biopolymers is always going to be part of the discussion. In this chart, I've compiled a comparison of relative costs of various biopolymers with those of legacy polymers. At the top are the legacy polymers made from oil. Biopolymers of all types are listed below. I've also included melt temperatures because this often determines a polymer suitability for a given application. And finally, on the right column, relative price information is shown. In this comparison, I've set the price of polyester as the basis of comparison and represented other prices as multiples of the polyester price. These prices will, of course, shift over time, and I've recently learned that legacy polypropylene in particular is beginning an upward move, so already the multiple for standard polypropylene looks like it will be higher than 1. I've placed asterisks against PHBH, PEF, and bio-based polypropylene to indicate that these polymers are particularly likely to see significant price reductions as commercial volumes grow. So we've covered the topic of biopolymers, but they're not the only tools we have in our toolbox. As we saw in earlier discussion, recycling can have a significant potential impact, and there are ways we can design our products to take advantage of these benefits. When it comes to recycled polymers, one of the first distinctions we encounter is between post-consumer recycled and post-industrial recycled materials. In discussions with customers, it often appears that post-consumer recycled materials are valued more highly, but I want to challenge that perception a little bit. Post-consumer recycled polymers have disadvantages against post-industrial recycled polymers in several different ways. They're more difficult to collect, so more of the available material ends up not being recycled. There are also environmental costs associated with fossil fuels burned to transport collected products to the recycling facility. For a long time, recycled products collected in the U.S. were shipped to China for processing, though that has largely ended. Additionally, consumer-level recycling results in polymer streams with reduced purity compared to industrial recycling streams. This reduces recycling efficiency and reduces the demand for the recycled product. So these are all ways in which recycling industrial waste streams is superior to consumer recycling. However, consumer-level recycling does offer a potentially significant benefit over industrial recycling. Because industrial recycling is more efficient and thus more cost-effective, and because it can be more easily regulated, industrial recycling can be expected to occur without additional intervention. But programs to facilitate and encourage consumer-level recycling are more likely to boost the buy-in of consumers who might otherwise not be active in recycling, and can help educate consumers in ways that also encourage reduced use, increased reuse, and more intelligent purchasing habits. So industrial recycling is more efficient, but consumer recycling is the area where bigger gains are possible. In either case, the purity and scale of the input stream is critical to recyclability, and this has some important consequences in fiber and fabric design. The first is that fiber blends are typically not recyclable. A 100% polyester garment can easily be recycled, and a cotton t-shirt can be composted. But a typical polyester cotton blend is not useful in either end-of-life stream. This also means that bicomponent fibers are often not recyclable. This is a particularly galling fact for me to have to mention because FIT has a significant focus on bicomponent fiber development and production. But we do have some bicomponent fibers that can be recycled, and we're working on more. FIT also has a focus on fibers incorporating high-performance polymers, but these polymers are usually more expensive and used only for niche applications that can support the cost premium. As a result, available quantities of these materials often fall short of those required for efficient recycling. Beyond conventional recycling, there are several new developments that take the concept further, and these can also improve the environmental profile of a fiber or fabric product. For instance, a new recycling process is available that builds the molecular weight of the polymer in the recycling process. So when polyester is used in a bottle, for instance, it has a high molecular weight that's reduced when the bottle is made. So recycled bottle polymer can't be reused in bottles because the molecular weight is too low. This polymer can be used in fibers, but the fiber process reduces the molecular weight even further, which means that recycled fibers can only be used in even less demanding applications. Eventually, the polymer's molecular weight is too low to be useful in any product, so it gets landfilled. This process is called downcycling. But if the recycling process can increase the molecular weight, this ends the need for downcycling, potentially extending recycling indefinitely and possibly ending the need to ever landfill the recycled polymer. There's also a newly announced process developed by Procter & Gamble that actually dissolves polypropylene in a benign solvent to produce a recycled polypropylene that's identical to the virgin polymer. That's a pretty neat trick since polypropylene is widely used because it's resistant to almost every solvent. But P&G say that their process can not only dissolve polypropylene, but that they use a safe, benign solvent to do it. Since the resulting product is identical to virgin, the benefits are the same, potentially extending recyclability indefinitely. Remember the class of biopolymers that have a negative carbon footprint as long as the carbon is sequestered in the product? Recycling technologies like these could multiply the value of those polymers by extending the sequestering to extremely long time horizons. A much older approach is the depolymerization and repolymerization of polymers in recycling. This also produces a recycled polymer that's identical with the virgin material, but so far this has proven to be costly and energy intensive. But development in this area continues, so there may yet be a breakthrough. Here's a recent development that I think is intriguing. There are at least 3 suppliers now offering recycled plastics that are curated by their source. That is, if you wish, you can specify in your product literature that your product is made with plastics taken from the ocean, along the shores of Indonesia, for instance. This is another opportunity to combine environmental responsibility with social responsibility. Finally, I want to point out that the whole point of learning about all of these opportunities is to be able to use them to design fiber and fabric products more intelligently. And this goes for recyclability as well. As I mentioned, FIT has a fundamental competence in unrecyclable bicomponent fibers, but we're working to redesign fibers in ways that mitigate or eliminate this problem where appropriate and where possible. A polyester, copolyester sheath core binder fiber, for instance, is more readily recyclable than a polyester and polyethylene binder fiber, and in many cases will deliver comparable performance. In addition to recycling, it can be worth considering the energy impacts of the fiber or the fabric design. There are a number of different ways to crack this particular nut. The first is to design products that require less to be used. In some cases, substituting a fiber with higher strength or higher surface area or other enhanced performance, depending on the application, can allow you to use less of the fiber with comparable performance. Another version of this is using more durable polymers so that the product lasts longer. It's also possible to reduce the fossil content in a fiber by displacing fossil polymer with renewable filler materials, as I mentioned earlier. The choice of polymers used or even the design of the fiber can reduce the energy required to produce a fabric. For instance, a binder fiber that activates at a lower temperature may reduce the energy consumption of a bonding oven, as a fairly simple example. It may be possible to make choices that reduce the transportation required, thereby burning less fossil fuels in transportation. Perhaps a lighter weight product would reduce transportation costs, or in other cases, depending on how it's transported, a denser product that requires less space could achieve the same result. Possibly a small effect, but at least steps in the right direction. It may also be possible to design a fabric to reduce the energy used in the end application, or to reduce the energy required to recycle or otherwise recover the product at the end of its useful life. Finally, some materials and some product designs may lend themselves more readily to incineration if recycling or degradation are not viable options. Incineration does pollute, but does so much less than might be imagined at first blush, and has the advantage of producing energy that reduces the use of fossil fuels. The last tool in the toolbox that I'd like to call your attention to is a concept called mass balance transfer. In a conventional manufacturing process, it's not uncommon for a producer to have access to a mixture of raw materials, some of which may be made from oil and others that may be bio-based or recycled or otherwise environmentally advantaged. For any number of reasons, it may be impractical for the producer to produce a dedicated line of green products from the green raw materials, so he has little choice but to make products using both streams, resulting in products that are sold without any claim to the benefits of a portion of the raw materials. Using mass balance transfer, though, the manufacturing process does not change, but the manufacturer simply determines the proportion of feedstocks that are environmentally advantaged and segregates the same proportion of his product into green products that are sold at a price premium. Of course, this has to be audited and certified by a disinterested third party. At a first glance, it may appear that this is nothing more than an accounting trick that doesn't really provide any environmental benefit and only serves to give the producer higher margins on some of the product. But the purpose of this approach, and the reason it has some support, is that the higher price the producer receives from doing this becomes an incentive for him to preferentially select the advantaged raw materials, which in turn increases their value and incentivizes the economic processes that produce them. If you're interested in this approach, BASF is one producer that is actively pursuing options along these lines. Now, initially, I had only 5 primary categories for discussing ways we can design our products to mitigate their adverse environmental impact. But there is a 6th category, which is all of the ideas that we don't know about yet. The problem is so big, we'll need to use all of them. It may be, too, that you have an idea that I haven't covered here, or even a novel way to use something I did cover. We're eager to talk to you, and there's a specific reason why. And that reason is that FIT is the best place for new fiber ideas to be born and grow to maturity. And I honestly believe I can say that objectively. Unlike most fiber producers, we didn't create FIT to be a commodity producer, but to be the most versatile and most innovative fiber producer in the world. So, for instance, we have the ability to design and produce fibers with a wide variety of cross-sections. And if we find a need for one not shown here, other shapes are possible. As I mentioned earlier, we also specialize in bicomponent cross-sections, and we have developed unique proprietary technology to give us unprecedented control over the cross-section designs we can achieve. Also, unlike most fiber producers, we're not stuck with a single polymer, but we can and do make fibers from a dizzying variety of materials, including the biopolymers we've discussed today. We like to say, if it melts, we'll try it. There are some exceptions, though. And in addition to all that versatility, we can further adjust the fiber's properties with selective inclusion of various performance-enhancing additives. When you combine cross-sections, bicomponents, polymer variety, and additives all together, we have a unique ability to develop and then produce a fiber with properties as close as possible to what the application demands. Finally, all of that versatility is backed up with a unique in the world pilot scale staple fiber line, which has been running continuously now for 25 years with something new every day. So we've seen a lot and have a lot of experience in turning ideas into fibers. And once a new fiber is developed, we have a lot of experience scaling that new fiber up to produce it commercially. Unlike many fiber producers, developing new fibers is not a way we complement our core business. For us, it is our core business. So that's why I say, again, I think I can say this objectively, that FIT is the best place to come with your ideas for a fiber that might do a better job of protecting the environment, and one that is uniquely appropriate to your specific process and your specific objectives.
Of course, no one technology is going to address every issue perfectly. It's a long and complex journey. The best we'll be able to do is to take the steps we can take today, implementing the solutions that are economically viable now and advancing toward the goal one step at a time. Looks like it might be even better up ahead. Why don't you join us? Let's find out.